Welcome to our introductory tutorial, Microbial Fermentations Governing Phenomena. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. Industrial fermentations make use of a wide variety of microorganisms, including bacteria, yeasts, and filamentous fungi, to produce valuable products at scale. These microbial cells are typically cultivated in stirred tank bioreactors, which can range in size from laboratory-scale vessels to industrial fermentors holding several thousand cubic meters of culture volume. Fermentation processes are widely employed across the food, chemical, pharmaceutical, and environmental industries. In these applications, microbial cells harness their complex metabolic pathways to grow and produce a diverse array of valuable products. These include small molecules such as ethanol, organic and amino acids, antibiotics, macromolecules including proteins, polysaccharides, DNA, viable microbial cells used as starters or probiotics, traditional fermented products like beer, yogurt. In addition to product synthesis, microorganisms also play a crucial role for water and waste treatments. When microbial cells are cultured in fermenters with nutrient-rich media, they consume key substrates, such as sugars, nitrogen sources, and, in the case of aerobic fermentations, oxygen. These substrates are metabolized and converted into microbial biomass in a range of fermentation products or metabolites. Throughout the fermentation process, the composition of the medium changes dynamically over time. Typically, this involves a decrease in substrates concentrations alongside an increase in biomass and product accumulation. These fermentation dynamics, the time-dependent changes in substrate, biomass, and product concentrations, are strongly influenced by several factors, including the microbial strain, medium composition, and fermenter operating conditions. Despite differences among microbial species, there are often similar patterns in substrate consumption dynamics during fermentation. For example, in batch fermentations, sugar concentrations typically decrease steadily over time, as cells actively take up and metabolize the available carbon source. When multiple carbon sources are present, microorganisms may display sequential, dioxic utilization, preferentially consuming one substrate first, then switching to the second only after the first is depleted. In aerobic fermentations, the dissolved oxygen concentration tends to follow a more complex trajectory. It declines rapidly during the fast growth phase, reaches a minimum, and may rise again as the primary carbon source is exhausted and cellular activity slows or transitions to another metabolic state. There are also striking similarities in microbial growth dynamics. As microorganisms consume nutrients, they undergo distinct growth phases, typically observed in batch fermentations. Lag phase, a period of little to no growth, during which cells adapt to the new environment. Exponential type phase, characterized by rapid cell division and a sharp increase in biomass. Deceleration phase, where the growth rate slows as nutrients become limited or inhibitory byproducts accumulate. Stationary phase, growth halts and the population stabilizes due to nutrient exhaustion or other environmental limitations. When multiple carbon sources are available, these growth phases may occur sequentially, with each phase corresponding to the utilization of a different substrate. While microbial growth dynamics often share common patterns across different species, significant differences arise in the dynamics of metabolite and product formation. As a result of their metabolic activity, microorganisms produce and secrete a wide range of metabolites, which can be broadly categorized based on their association with growth. Growth-associated metabolites, such as ethanol or lactic acid, are typically produced during the fast growth phase, with their concentrations increasing steadily over time in batch cultures. Non-growth associated metabolites, including amino acids, antibiotics, and, in engineered strains, recombinant proteins, are generally synthesized after the rapid growth phase, often during the stationary phase, when nutrients become limited and growth slows or stops. In some cases, microorganisms may also excrete metabolites that are later reassimilated as secondary carbon sources. A classic example is ethanol production by yeast, where ethanol is secreted during fermentation and later consumed once the primary sugar source is depleted. The dynamics of product and metabolite concentrations are highly sensitive to the fermenter operating mode. Significant shifts in fermentation behavior can occur when transitioning from batch to fed batch or continuous operation, particularly under carbon or nitrogen-limited conditions. Under substrate-limited conditions, two contrasting effects are often observed. First, the reduction in growth-associated metabolite production. Lower substrate availability decreases metabolic overflow, leading to reduced formation of byproducts, such as ethanol in fed batch or continuous yeast fermentations, operated under sugar-limited conditions. The second effect is the enhancement of non-growth associated product formation. Conversely, slower growth or nutrient limitation can stimulate the synthesis of secondary metabolites, such as antibiotics, and recombinant proteins, which are typically favored when cells redirect their metabolism from growth to product formation. Differences in fermentation dynamics often emerge during scale-up from laboratory to industrial-scale fermentations. One of the most notable changes involves the time profiles of dissolved oxygen and carbon dioxide, which can vary significantly with scale. These shifts can influence microbial growth rates and alter metabolite production patterns. In this tutorial, we will explore a central question. What are the fundamental biochemical and physical phenomena that govern microbial conversion dynamics in fermenters operated under different modes and at varying scales? In fermenters, the time-dependent variations in the concentrations of fermentation components are governed by three fundamental phenomena: microbial conversion reaction, mass transfer, and fluid flow. The primary driver of these concentration changes is cellular metabolism, specifically the rates at which cells consume substrates, grow, and produce metabolites and products. In addition, physical phenomena play a critical role in shaping culture dynamics. Mass transfer, particularly the rates at which oxygen and carbon dioxide are exchanged between the gas phase and the culture medium. And fluid flow, the circulation and mixing of liquid elements within the bioreactor. In microbial fermenters, the primary factor driving process dynamics is the microbial bioconversion reaction, the transformation of substrates into biomass and desired products. The overall duration of the fermentation, as well as the final concentrations of cells and products, is largely dictated by key cellular activities, including growth rate, nutrient uptake, and metabolite or product formation. These biological activities are highly dependent on the specific microbial strain or cell line used, as different organisms exhibit distinct metabolic capabilities and performance characteristics. Cellular-specific rates are dependent on many environmental parameters that generally change during cultures. First, the concentrations of the substrates or nutrients in the culture medium. There are the concentrations of carbon source, nitrogen source, dissolved oxygen. Second, the concentrations of the excreted metabolites and products. Third, physicochemical variables such as the medium temperature, pH, and osmolarity. Cells may also be affected by the physical stresses induced by the medium stirring. Cellular rates vary significantly throughout the course of fermentation. Typically, specific rates, growth rate, substrate uptake rate, are low during the lag phase, as cells adapt to the environment. They reach their maximum during the rapid growth phase. Afterward, these rates gradually decline as nutrients become limiting or inhibitory byproducts accumulate. In some cases, particularly with non-growth associated products, a specific production rate may increase upon induction, triggered by factors such as nutrient limitation, temperature shifts, or chemical inducers. Variations in cells' specific rates are caused by changes in medium composition, temperature, or medium pH. Substrate limitations play a critical role in shaping microbial fermentation dynamics as they directly impact cellular metabolic activities. Limitations in key substrates, such as carbon sources, nitrogen sources, or dissolved oxygen, can lead to a reduction in cell growth rate and growth-associated product formation due to restricted metabolic activity. Conversely, in some cases, substrate limitation can enhance the synthesis of non-growth associated products, such as secondary metabolites or recombinant proteins, which are often favored under nutrient-limited conditions. Another important factor influencing microbial fermentation dynamics is the accumulation of products and byproducts in the medium, which can significantly affect cellular metabolic activities. As growth-associated and non-growth-associated metabolites, as well as dissolved carbon dioxide, accumulate over time, their increasing concentrations can lead to inhibitory effects on cell growth rates due to metabolic stress or toxicity. Product formation, particularly when key enzymes or pathways are downregulated in response to product buildup. In many fermentation processes, fermentation kinetics are strongly influenced by physiological transitions as cells shift between distinct metabolic states during the culture. These key states include an initial lag phase, where inoculated cells adapt to the new medium and environmental conditions, resulting in slow or no growth. A rapid growth phase, characterized by active cell division and biomass accumulation. A production phase in which metabolic activity is redirected toward the synthesis of desired products rather than biomass. The transition into the production state is often triggered by external factors such as the addition of an inducer, a temperature shift, or nutrient limitation. Physiological transitions, from the growth phase to the production phase, are often accompanied by changes in microbial cells' morphology. For example, filamentous microorganisms can shift from dispersed mycelial forms to compact pellet structures, a morphological change commonly observed during antibiotic production and other secondary metabolite processes. How are cellular reaction governing phenomena scaled up? Among the different phenomena influencing microbial fermentation, cellular activities are typically the most directly transposable from small to large scale. This is because cells respond primarily to their immediate microenvironment, the local concentrations of nutrients, metabolites, and dissolved gases, rather than to the total culture volume. As a consequence, similar cell growth and metabolic kinetics can often be reproduced across scales, provided that comparable microenvironmental conditions are maintained. However, certain scale-dependent effects can introduce variability. For example, increased shear stress at larger scales may lead to cell death. Differences in the physiological state of the inoculum between scales can also influence the length of the initial lag phase, affecting early fermentation dynamics. The kinetic laws that describe microbial cells rates as a function of environmental conditions are presented in the tutorial, Microbial Cells Kinetics. Mass transfer is the second fundamental phenomenon governing microbial fermentation dynamics, primarily controlling fermenter aeration. Aerobic fermenters are continuously aerated to supply oxygen, essential for cellular metabolism, and to remove carbon dioxide. This constant gas exchange is necessary because of the low solubility of oxygen and carbon dioxide in aqueous culture media. The supply of oxygen in the fermenter occurs in three stages. First, oxygen is introduced into the fermenter through the inlet air system. Next, a portion of the oxygen transfers from the air phase into the liquid medium. Finally, the cells present in the medium consume the dissolved oxygen for metabolic activities. Similarly, the removal of carbon dioxide follows a sequential process. The cells in the medium produce carbon dioxide as a metabolic byproduct. The carbon dioxide then transfers from the liquid medium into the air phase. Lastly, the outgoing airflow carries the carbon dioxide out of the fermenter, effectively stripping it from the system. Oxygen transfer from the gas phase into the liquid medium occurs through three consecutive steps. Transport to the interface. Oxygen moves from the bulk gas phase to the gas-liquid interface by diffusion and convection. Dissolution at the interface. Oxygen molecules cross the interface and dissolve into the thin liquid layer adjacent to the surface. Transport into the bulk liquid. Dissolved oxygen diffuses and is convected from the surface layer into the bulk culture medium. The rate-limiting step is typically the transport of oxygen across the liquid boundary layer into the bulk phase. This occurs through both molecular diffusion and convective mixing, with the latter strongly dependent on local fluid velocities near the interface. The oxygen transfer capacity of a fermenter is primarily determined by the gas-liquid interfacial area available within the system. This includes the surface of the culture medium exposed to the headspace, the surface area of dispersed air bubbles, which generally provides the dominant contribution. The bubble surface area depends on the airflow rate supplied to the culture, the type of sparger, which strongly influences bubble size distribution. In addition, oxygen transfer capacity is affected by the efficiency of oxygen transport within the liquid phase, which depends on convection and mixing intensity, that is, the fluid velocities and turbulence within the medium. In some fermentations, there is a significant reduction in the interfacial air-liquid surface area and consequently in oxygen transfer capacity over the course of the process, often due to changes in medium composition. This can occur, for example, when medium viscosity increases as a result of polysaccharide excretion or the accumulation of filamentous biomass, when air bubbles coalesce, triggered by the use of antifoam agents. Both phenomena contribute to the formation of larger air bubbles, which reduce the total gas-liquid interfacial area, thereby impairing oxygen transfer efficiency in aerobic fermentations. The dissolved oxygen concentration is determined by the balance between the two consecutive oxygen transfer from the air to the liquid phase and oxygen consumption or demand by cells. During a batch fermentation, the oxygen consumption rate initially rises during the cell growth phase and often reaches a maximum and further declines. To maintain the balance between oxygen transfer and consumption, the dissolved oxygen concentration decreases during the rapid growth phase, reaching its minimum when oxygen consumption peaks. It then gradually increases as the fermentation oxygen demand decreases. In a similar manner, the dissolved carbon dioxide concentration is determined by the balance between the two consecutive CO2 production by cells and CO2 transfer from the liquid phase to the air. During a batch fermentation, the cellular CO2 production rate increases during the rapid growth phase, often reaches a maximum, and subsequently declines as growth slows and metabolic activity decreases. As a result, the dissolved CO2 concentration rises during the rapid growth phase, peaks when CO2 production is at its maximum, and then gradually declines. In fermentations involving filamentous microorganisms that form pellets, additional mass transfer limitations can significantly influence process dynamics. The diffusion of nutrients and dissolved oxygen into the interior of the pellets can become a rate-limiting step, for both cell growth and metabolite production, leading to the formation of concentration gradients within the pellet structure. In particular, oxygen limitation inside the pellet core can cause cells to shift from aerobic to anaerobic metabolism, altering cell activities and product formation rates. How are mass transfer phenomena scaled up in fermenters? During scale-up, mass transfer behavior, particularly for oxygen and carbon dioxide, cannot be directly translated from laboratory to industrial scale fermenters due to differences in hydrodynamics and gas bubble circulation patterns. As a result, both the mass transfer capacity and the resulting dissolved oxygen and CO2 concentration profiles can vary significantly with scale, potentially impacting microbial activity and product formation. This challenge is further amplified in fermentations involving filamentous microorganisms. Due to scale-dependent flow and mixing patterns, pellet size distributions may change, affecting internal diffusion of nutrients and oxygen within the pellets, and leading to varying degrees of mass transfer limitation across scales. The third fundamental phenomenon influencing cell culture dynamics is the flow of the medium within the fermenter. The flow field is defined by the distribution of fluid velocities inside the vessel. It depends on impeller geometry, shaping whether circulation is predominantly radial or axial. Agitation intensity, power input, set by the stirring rate, which governs overall mixing strength. Medium rheology, particularly viscosity, which can change during culture as biomass and metabolite concentrations increase. The intensity and distribution of fluid velocities play a crucial role in fermenter performance, influencing several key aspects of the process. Firstly, they determine the mixing efficiency within the bioreactor. Effective mixing ensures a uniform distribution of cells, nutrients, and dissolved gases throughout the culture medium. This helps to prevent the formation of poorly mixed zones where local concentrations of oxygen and nutrients may be significantly reduced, potentially leading to suboptimal growth conditions and non-uniform product formation. Second, fluid velocities within the culture medium directly affect convection-driven mass transfer efficiency. Higher fluid motion enhances the rates of oxygen transfer into and carbon dioxide transfer out of the liquid phase. Consequently, the intensity of mixing influences the dissolved oxygen and carbon dioxide concentration profiles during fermentation. At higher stirring rates, one typically observes a smaller decline in dissolved oxygen and a reduced accumulation of dissolved carbon dioxide. Fluid velocity patterns within a fermenter can have a direct impact on cellular activity and viability. Velocity gradients between adjacent fluid layers generate shear forces, which can be particularly damaging to shear-sensitive cells as filamentous microorganisms. In stirred systems, cells are also exposed to turbulent eddies. When the eddy size approaches or becomes smaller than the cell size, cells can experience intense localized shear stress. How are fluid flow phenomena scaled up in fermenters? During scale-up, fluid flow behavior cannot be directly transferred from laboratory to industrial scale fermenters due to significant changes in radial and axial velocity patterns within the vessel. As a result, key hydrodynamic parameters, such as mixing efficiency, convective mass transfer intensity, and shear stress experienced by microbial cells, can vary considerably with scale. These differences can, in turn, affect microbial activity, metabolic performance, and overall product formation. In summary, in this tutorial you learned that in fermenters, the time-dependent variations in fermentation component concentrations are governed by three fundamental phenomena: microbial reaction, mass transfer, and fluid flow. The primary driver of fermentation dynamics is the microbial reaction, characterized by the rates at which cells consume substrates, grow and produce metabolites or recombinant proteins. In addition, physical phenomena critically shape the cell's environment: mass transfer, governing the exchange of oxygen and carbon dioxide between the gas phase and the liquid medium, and the diffusion of nutrients inside microbial pellets. Fluid flow, determining medium circulation, mixing efficiency, the intensity of convective mass transfer, and the shear stresses experienced by cells. Together, these biochemical and physical processes dictate the dynamic behavior of nutrients, biomass, and metabolites throughout fermentation. They also establish the fundamental limits of achievable performance, including maximum cell density and final product concentration. The fundamental phenomena of microbial reaction, mass transfer, and fluid flow provide the basis for knowledge-driven simulation models in bioprocess engineering. Such models allow the prediction of dynamic variations in nutrients, cells, and metabolites across different bioreactor operating modes. They are powerful tools that support the digital scale-up, control, and optimization of microbial fermentation processes. The development and application of fermentation simulation models will be explored in greater detail in an upcoming tutorial. If interested, you can gain a deeper insight in microbial fermentations by enrolling to the online courses, Introduction to Microbial Fermentations Technology and Engineering, and Digital Scale-Up and Optimization of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.